Welcome. Today, very good morning to all of you. I hope you guys are doing good. And we begin our lectures on data structures. As you know that we are passing a time where we need to prepare ourselves very well and we need to continue all our activities. You guys are making very good progress, and let's begin our discussion. The next talk I'm going to tell you about is our agenda of discussion. If you see, our target is to discuss 20th March. Today we talk about stack application, discussion on tree, final exam plan, project presentation plan, and do some exercise. The coming class, 27th March, we discuss on binary search tree, we discuss on graph and do some exercise, and by this process we get ourselves ready for the final exam. Alright, so let us proceed to talk about the final exam plan. As you know, it will be a very interesting question. You have seen the previous year question papers. We have some problem and you analyze the problem and you apply the knowledge of tree and binary search tree and heap, and also we need to do some problem solving using graph. So you guys will be getting ready for the final exam, and let's have a very good practice and preparations. I will actually put a lot of code in Google Classroom today, and CR is taking care of all the attendances. CR will compile an Excel file and ultimately give me in the Google Classroom. Alright, so let us proceed to talk about the next one, is the project presentation plan. So you have done already one presentation, and I'm very happy that you made a very good presentation. But right now what you have to do is, since you are at your hometown and you're working on your own, but you are a virtually connected team. So what you will do for your project, you propose a data structure and design an implementation model. You implement that project using C. You capture your operational movie, screen capture movie, and also take some of your pictures, maybe individual, maybe in a team, or maybe in a virtual setting, and then upload everything in your Google site. And once the Google site is updated, you submit the link. The deadline is Tuesday 31st March 2020. So I will take a look at each of the Google site to understand your progress, and hopefully we'll be meeting before the final exam to finalize our remember we talked about the promo video. We will do that after everything settles down. All right, so wish you all the best. Let's proceed to our discussion of today. We need to talk about tree. Tree, as you understand, that is a very dynamic data structure. So far we talked about linked list, which is the basic foundation, the building block for data structure. And you remember that we talked about stack is a last in first out, but they are all linear data structure. The first nonlinear data structure today you come across is tree. Tree is a nonlinear data structure, and like tree, you may have child, you may have 3 child, you may have 4 child, you have a root node, and you have child. So let's proceed to our discussion agenda. We need to talk about roughly some of the tree terminology. What is a tree? Why tree? We talk about general trees and their implementation, semi-binary trees, semi-implementing trees, binary trees, and implementation and application of binary trees. Our target is also to see the tree traversal technique also today. So we finish the foundation of tree data structure today. Now, question is, what is a tree? As you understand, the T is a finite set of nodes, and you can see that clearly. These nodes are here, and these nodes are together with a finite set of directed edge. If you see on the left hand side, you have a root node A. This is the root node, and you have a left child and the right child, and you have all the childs coming, but you can understand one of the node has 3 childs, and another node has 2 child, but these nodes are actually the leaf nodes. That means if there is no further node, we call it leaf node. Nodes are, how many nodes we have here? Altogether 8 nodes. That means the size of the tree is 8. And when we have terminologies, you can see edges. These edges are AB, AE. You can see it clearly now. How many edges we have altogether? We have 7 edges. We are considering the root node. So there is a direct path, and you understand when it comes to tree terminology, tree satisfies the following properties. It has one designated node. You actually call it a root node. And this root node is only one. That means a tree cannot have a multiple root node. Like you have seen on the right hand side, is not a tree because it has two root nodes. But it's also, you can see here why it is not a tree. Every node except the root has exactly one parent. A node, you can see here 4 has two root, 2 parent. So this is not allowed. So a node may have 0 or more children. Some of the nodes like 3, you do not have any children, but some of the nodes you have 3 children. So this is a kind of the property of a tree. So tree is a very dynamic data structure. But you can understand that why we want to look at tree, because in the nature we have so much of tree, and every tree follows a very specific pattern of organization of data. And you will see soon that why tree is so important. So let's proceed to look at some of the terminology. When we talk about the tree, you have some of the terminologies coming in. The ancestor and the proper ancestor. You can understand ancestor of G, that means who are the fathers. CA, that means A, C, and G is the ancestor of G. But if you look at proper ancestor means the node without the node itself, the father. Like you can see here, B and A is the proper ancestor of E. And ancestor, like ancestor, we have also descendant. Descendant means from parent to child. We have proper descendant and descendant. Like we have ancestor and proper ancestor. So proper ancestor of node, any node excluding the node, excluding the node on the path from the root to the node. So one of the terminology you come across this. Descendant, as I just directly told you, that descendant and the proper descendant. Who are the proper child? So subtree is another concept. Subtree is the tree has 2 sub-branches. We sometimes call order of the tree is number of subtrees. So what we see, this tree has the order 2 because it has 2 subtrees, all right? So this is something very, very important. When you look at a tree terminology, you have parent, you have grandparent, you have a grandfather, you have a great-grandchildren, you have a subtree, you have proper ancestor, you have proper descendant, you have an empty tree also. That the root node is null. That means all subtree references are null. So, you may have something like this. Now, coming into very important terminological degree. What is a degree? The number of non-empty subtree of a node. Like each of the node D and B has degree of 1. You can see D has only 1 subtree, and you can see the other one is B. B has also 1 subtree. Each node A and A has degree 2 because you see E has 2 subtree. So you can understand a leaf means a node with a 0 degree is a leaf. You may have internal organizations and so on. Alright, so you have come across the degree of a tree. Now we are going to look at the level and the height. You see the level or depth of a node is the path. You can understand the depth is from the root to the leaf. That means we talk about the number of edges from the root to B, and height is from the leaf node to the root. So you can understand, looking at this tree, you can see it's the first one is a level 0, then level 1, level 2 and level 3 and so on. And the height of the tree is 4. Why? Because you can see the longest path 1, 2, 3 and 4. Height of the tree is the height that you see from leaf means I'm talking about K to A. If you see how many edges you have, 1, 2, 3, 4. So there are 4. So altogether you can say height of the tree is 4. But if you consider height of the node C is actually 1, 2, 3. So there are 3 actually edge. So any question here? I'm sure you have no question, because so you understand the difference between level or depth and height. What is depth? Depth is the longest path from the root to the leaf. So root to leaf, the longest path is depth or level. And what is height? Height is the longest path from leaf to root. It may be leaf to node or leaf to root. Alright, so let's proceed to the next. So why tree? Trees are very important data structure in computing. You can understand, you can organize data like this. Hierarchical organization. We have organizational structure in every company, which looks like a tree. That means you have a managing director, then CEO and the CTO and the managers and so on. So in the practical life, we have lot of organizational of information which is based on tree. So that's why tree is very important. And you can have textbook organization like this, chapters and so on. So how do you actually define a data structure for the tree? You can see here, we create a structure, and this structure is a node which you can understand that we talk about binary tree. We have 2 child, one is a left child and another is a right child. So we have 2 pointer referring to left and right. And by this, what we do when we actually create the implementation, if it is 2 child, you can have this kind of binary representation. If it is a 3 child, you have this type of binary representation. It depends on how many child do you have for your tree. So the general tree representations are very, very important. To cut n-ary tree means we are talking about n-ary tree is an order tree. It is either empty or it consists of a root node and n non-empty array subtree. So you can see binary means 2 subtree, and tree array, sometimes we call tertiary tree. You have 3 subtrees, and you have quad and hexa and so on. So n-ary tree means you're talking about trees which is having n number of subtree. Alright, so binary tree, as you know, n-ary tree for which n is 2. That means you can have either it is an empty tree or it consists of 2 subtree. One is the left, another is the right subtree. Alright, and you take a look at this example. You have a root node 5. How many leaf node you have? 9, 5, 7 is the leaf node. What is the degree of 7? Degree of 7 is 0. But what is the degree of 2? Degree of 2 is 2. What is the degree of 5? Degree of 5 is 2. So you can understand. And a 2 tree, sometimes we call a 2 tree is either is an empty binary tree or a binary tree, where this leaf node has 2 non-empty subtree. So example of 2 tree, you can see node A has 2 subtree, node B has 2 subtree, node E has 2 subtree. That means every node has 2 subtree. An example of a binary that is not a 2 tree, you can understand why. Because C has only 1 subtree, F has 2 subtree. So it is not a 2 tree, but it is a binary tree. Now can you tell me what is the size of this tree? This tree, you have to count how many nodes you have. So how many nodes you have? 3 through 6, 7, 8, 9, 10, 11, 12. The size of the tree is 12. It is actually a binary tree, but it has a size of tree. Sometimes we have 2 types of tree. We say complete binary tree and full binary tree. Full binary tree means you know every node has 2 child. So full binary tree means every level has that number of childs. For example, if the level is 2, 2 to the power of 2 means 4 child. If the level is 3, 2 to the power 3 means you must have 8 childs, and so on. So it is a full binary tree, but if it is a complete binary tree means the 3 childs are filled from left to right. Well, I'm going to show you that also. So you see a full binary tree here. You can see right now, we just discussed about it. And it's a full binary tree is an empty tree, or you have that number of childs. And an example of a full binary tree, you can understand it's a full binary tree. But if you look at a binary tree, full binary tree is this calculation is a non-empty full binary tree is log base 2 n plus 1 is equal to 1. And if you see the binary tree, a complete binary tree, as I was mentioning, that it is either an empty binary tree or binary tree, it's filled from left to right. You can see here, this one is a complete. Why? Because A, B, C, then D has 2 subtree, E just 1, there is going to be another one. So it's actually getting filled from left to right, and we call it complete binary tree. But if you look at this one C is incomplete. So that's why it is non-complete. It's a binary tree, but it's not a full binary tree. It's not a complete binary tree. I hope you understand this. Now, so you can understand the difference between these trees, showing the growth, how you are creating, and it's gradually building up a complete binary tree. You add first one, then fill from left to right. So you see you are filling from left to right, and look at this one, you fill from left to right, and finally you come into this. So you keep adding. Suppose if you bring a new child, where you are going to add, you're going to add here, So this particular child is going to create the tree as a complete binary tree. All right. So binary tree, we already have an idea that how many nodes the binary tree of 5, h, and you have the maximum number of node is h plus 1. For a linear tree, or for a full binary tree is actually 2 to the power of h plus 1 minus 1. Minus 1, why? Because there is a root node. For a binary tree with n nodes, you can actually have a calculation like this. I give you typically showing you a picture that how actually you create this data structure. You define the tree first, the node, and then allocate the memory, malloc. Then you have to allocate for the left child and for the right child and assign the value. And I'm sure you look at this particular picture on your right and look at the code and analyze and post me question in the Google Classroom. We can discuss about it. So binary implementation, a tree is such that you have to have a null values, key left and right. And that's actually how we have done it already in the code I show you here. So in most cases, it's represented like this. It's a tree, but how do you represent? It's like this, because you don't have any left. Somewhere you have left, somewhere you don't have right. So right you don't have means null. You can see C. For example, look at the C node and look at C here. You can see that this C has no left and right, so both are null. All right? I'm sure you understand this. So these are actually typical applications, and we have decision trees, we have many expression trees, and we have Hoffman coding is based on actually binary tree. We are